Multi-hazard risk assessment of heritage buildings. I am Andres Winson C. Oreta of De La Salle University. Why assess heritage structures? Okay, first of all, there are change in use, increase in load capacity. As you can see in these images, in buildings along the heritage zone in Iloilo, there are buildings wherein billboards were installed. Some commercial use for results to heavier loads due to storage of goods and supplies, and some buildings have added mezzanines. Hence, the live load on these structures changes. Heritage structures were built based on outdated design codes. And in the present codes, specifically for seismic analysis and design, the following issues are very important, like vertical irregularities, as can be observed in some heritage structures, plan irregularities, like in these existing buildings, the use of unreinforced masonry, which results to brittle failure, inadequate steel reinforcements, which lacks ductility of members, and of course, seismic detailing of RC members. Another reason is due to deterioration, due to time, such as due to corrosion and water. Shown in these images are exposed and corroded steel in the beams and slabs, material deterioration, concrete cover spalling. So there's a need for a rapid hazard risk screening, especially when we have a big population of buildings. So the objectives are to group the buildings according to asset, value, importance, or use, to rank the buildings according to risk screening, score rating, to prioritize which buildings need immediate attention for a more detailed structural evaluation based on the risk rating, and to decide what action must be done on the buildings, like retrofitting, strengthening, repair, or maintenance. The framework for risk assessment follows the hazard vulnerability asset framework, wherein the hazard is assessed, the vulnerability of the building is also assessed on their impact on the asset, in this case, the heritage buildings. Risk is then evaluated. It is a function of the hazard and vulnerability of the asset or the heritage structures. Asset value assessment involves associating a value, not necessarily monetary, to existing structures. Heritage is multivalent, meaning assigning a value to heritage structures is a challenge because different values can be ascribed to a heritage structure. The value can be historical because the asset is associated to past events or because it is old. It may be aesthetic because the asset is beautiful and a fine work of architecture. Economic because it is a real estate property and provides income to the community. Political because it may represent a social order or class. Tourism because it is recognized landmark and attracts tourists. Or spiritual because it is a place of worship, especially if these are churches. So based on these various asset values, there have been various proposals as shown in this table. And each proposal incorporates specific parameters as shown, like age, use, and others. Okay, this is a simple example of an asset value assessment which was implemented in the graduate research of DLSU and the undergraduate thesis of the DLSU CPU collaboration. An example of an asset value is shown wherein architectural value, historical and heritage value, tourism value, and commercial value are considered. And the value is basically qualitative, no? Wherein a group of experts were asked to assign specific values, whether the value is low, medium, or high on the following parameters. Like architectural value is the building captures the architecture, design, and culture of the past generation. A2, the building's architecture blends beautifully with the city's culture. A3, the building's architecture is eye-catching and stands out among other buildings. So based on this criteria, the building is assessed on architectural value. Historical and heritage value. The building has heritage value locally, nationally, or internationally. The building has a history that is worth telling and preserving to the new generation. And the building's history strongly reflects the cultural heritage. Tourism value. The building is a must-see for locally international tourists. This building attracts local international tourists. The building is well maintained and not an eyesore to the tourists. And commercial value. The building stimulates economic activity. Adaptive reuse of the building supports local business. The building is often visited for its goods and services. So for each asset value, a score is assigned, and they were multiplied by weights. These weights can be determined by experts or can be conducted using and assigned using a survey. And a corresponding value can be obtained. Based on that asset value assessment, if you have a group of buildings like shown in this picture, each building has a corresponding asset value and they can be ranked, like in this study of the heritage structures in Iloilo. Now, the asset value assessment will be improved by the Cherish team under the UP Visayas Research Group. Hazard assessment. In hazard assessment, you want to know the following characteristics. The magnitude or size of the hazard. If for an earthquake, it may be ground acceleration, it may be fault distance. For typhoon, it might be the wind speed. For flood, it may be the flood depth. The frequency or return period used in the assessment is important. Amplifying factors. For example, for earthquake, soil type is very important in assessing the hazard. For typhoon, the terrain is important. And for flood, of course, the elevation and the nearness to high slopes is also important. Seismic hazard profile, for example, in Iloilo, can be assessed using various tools. For example, the peak ground acceleration of the site can be assessed using the Philippine earthquake model. The wind hazard profile can also be assessed. Okay? There are data from PAGASA, and in the National Structural Code of the Philippines, there is a map of contours of wind speeds, no, for various types of occupancy. For the lowest or standard occupancy, Iloilo has a wind speed of 240 to 250 kph for 15% probability of accidents in 50 years. Seismic hazard assessment and parameters. So in seismic hazard assessment, some of the parameters that you may consider is the fault distance. Okay, so a building which is has a distance less than 5 kilometers can be assessed as high risk. A building with a distance of 10 kilometers or more can be assessed as low, and in between will be a medium. One tool that you can use is, of course, the FIVOL's fault finder. The peak ground acceleration is describes the intensity of an earthquake. Okay, and an earthquake with destructive intensity has approximately a PGA greater than or equal to 0.2 G. An earthquake which is classified as weak to moderate intensity may be identified as one with PGA less than 0.02 G, and in between will be the medium. Okay, one tool for determining the peak ground acceleration for rapid assessment is, of course, the Philippine earthquake model and the spectral acceleration maps PH. The soil type, the seismic hazard parameter soil type, is another parameter for seismic hazard assessment. Soft soil like type E and F are classified as high, and hard rock and dense soil type A and B are classified as low risk. To determine the soil type, you can also use the Philippine earthquake model, where it represents the velocity, the shear wave velocity, and there is a table wherein the soil type has its corresponding shear wave velocity. Vulnerability assessment. Vulnerability is the degree of susceptibility of the structural and non-structural elements of the building to specific hazards. Okay, first of all, it is not a measure of safety, but it is related to the possible weakness of the building. As in Filipino, it is termed as kahinaan. Okay, so a building that possesses many vulnerable elements has a greater risk to perform poorly to the specific hazard. And again, for a rapid assessment, a qualitative and semi-quantitative vulnerability assessment can be developed. So what are these vulnerability parameters? First is the building material. So depending on the building material, the vulnerability of the structure with respect to earthquakes can be assessed. Okay, so high vulnerability are unreinforced masonry. Medium will be RC and steel, and low will be timber. And this is related to the weight or the mass of the material. The heavier the material, the higher will be the risk. The irregularities, plan irregularities, buildings with irregularities like in this picture are classified as high risk, and buildings which are regular in shape like square buildings, circular buildings are classified as low. And based on earthquake damages, buildings which are irregular usually fail due to torsion. Vertical irregularity type, like in these images, are highly vulnerable to ground shaking. So buildings with this type of irregularities are said to be highly vulnerable. Buildings which are regular are, of course, low vulnerability. So in this example, this is a building with a soft story. No? A soft story like this, the structure, the first and I think second story buildings, floors collapsed during the Luzon 1990 earthquake. Pounding effect is another concern, especially for building two buildings which are too close with each other. So buildings which have a high gap, like 16 centimeters or higher, have low vulnerability, and buildings which has almost no gap, like in this figure, have high vulnerability. The number of bays in the short direction. Okay, this is the short direction. The lesser the number of bays, the higher will be the vulnerability because it results to a slender structure, which is an irregularity also. And this is an example of a building with a very high vulnerability with respect to the number of bays. It's a very long structure, slender structure, which is classified as irregular. So based on those parameters, uh, rapid seismic risk screening form was developed considering the following. So the first part is the hazard parameters, no? So which includes the fault distance, the peak ground acceleration, and the soil type. Again, qualitative assessment of low, medium, and high can be assigned to each of these parameters, and they are multiplied by corresponding weights. And after multiplying, you take the sum, and you will obtain the hazard rating. Vulnerability parameters in this particular checklist, there are 8, which includes the following. The code year built. So a building which is built before design codes were developed, of course, have higher risk. Plan irregularities, vertical irregularities, building proximity and pounding effect, the building height, the structural system, material, the number of bays in the short direction, and the column spacing. Again, each parameter is assigned a value of low, medium, and high multiplied by the weight to get the rating, and then take the sum, and you will get the vulnerability rating. The vulnerability rating is modified by modifiers related to building condition. No? So this building condition includes deflection. Is the building inclined? Are there visible deformation in beams or columns? Cracking in walls or columns? Are there leaks on walls? Corrosion? Visible inclined cracks or columns? Or many visible cracks on walls? Fire experience, if the building was burned, not repaired, burned but repaired. Finishing conditions on the exterior walls and the interior walls, and additional loads. Some floors are used as storage or goods and equipment. There was an additional floor or mezzanine. So based on the existence of this building conditions, no, a modifier is assigned. And this modifier is multiplied to the vulnerability rating, and the structural vulnerability rating is now obtained. So if there are no building conditions modifiers, then the vulnerability rating is equal to the structural vulnerability rating. Otherwise, it will be increased depending on the modifier, which is greater than or equal to 1. So the hazard and the structural vulnerability are now combined, in this case, a simple product, to obtain the seismic risk index. For this particular building, the seismic risk index is obtained to be 3.56, which is under the medium seismic risk classification. Let's go into wind hazard assessment and parameters. In the previous study, the wind hazard parameter used is related to zones, but this is not anymore, or this was already updated by the National Structural Code of the Philippines, so in the 2015 edition. So the present checklist is now updated using the latest code. And this is the latest code. So in the latest code, we have, instead of wind zones, we have now wind contours. And to categorize the hazard as low, medium, and high, the following table was used. No? So high, when the maximum wind speed is greater than 280 kph. Medium, when the wind speed is between 225 and 280. And low, when the wind speed is less than 225 kph. Pag-asa has a wind speed of 220 kph for a strong or a super typhoon, which is still less than the 225 kph value. Another parameter for wind hazard is the building vicinity, as shown in these figures. No? So a building which stands on a flat terrain, unobstructed, will experience stronger winds, no? No? Especially at the lower level, no? As shown here. High wind speeds for flat terrain. But buildings which stand side by side with tall buildings, say mountains, urban, and numerous obstruction, the wind speed usually occurs at the higher level. Hence, the risk is lower. So what are the wind vulnerability parameters for buildings? The roof type is a parameter. It was observed that roofs which are monoslope, okay, one slope or flat, experience higher wind speed and uplift, like so, like in this figure. Roof types which have four slopes or hip roof, like in this example, experience lowest uplift, as shown in these images. And of course, gable roof to slopes, okay, higher with respect to four slopes, but lower with respect to monoslopes. The roof slope is another parameter. So if there's a slope, slopes less than 30 degrees or flatter experience more uplift than slopes with 30 to and 45 degrees experience less uplift. So flat roofs usually experience uplift forces, but slopes like 30, 45 experience an uplift on one side and a push or a downward pressure on the other side. The building enclosure is another wind vulnerability parameter. Buildings which are open, no, will experience uplift pressure, and wind inside which enters the building will push and will add additional pressure on the envelope. But buildings which are fully enclosed will experience only, of course, uplift pressure along the building envelope and a push on the other direction. Wind vulnerability parameters Of course, the roof material. The lighter the material, the higher will be the risk. The heavier the material, the lower will be the risk. Modifiers for the vulnerability includes overhangs like this. Because overhangs, there will be push downwards and uplift at the top. Parapets also are additional vulnerability. No? So it can be a push here or a push on the other side, and it can be a pull on the other side also. So based on those parameters, another checklist, rapid wind risk screening, was developed considering the hazards. And for wind hazard, the basic wind speed is considered using the NSCP 2015. The building vicinity can be determined by visual or site inspection. And the soil foundation type can be determined using also the earthquake model, Philippine earthquake model using the shear wave velocity. Again, the scores are assigned and multiplied by the weight to obtain the rating, and a sum will result to the hazard rating for wind. The vulnerability parameters includes the roof type, whether flat or four slopes, the roof slope, the number of stories, the roof material, building enclosure, building wall materials, structural framing, plan irregularity, and vertical irregularity. Scores are assigned for each parameter, multiplied by the weights to obtain the rating, and the sum results to the wind vulnerability rating. The wind vulnerability rating is modified using the modifiers, which includes the extensions. No? Are there overhangs? Are there parapets? And the modifier is multiplied to the vulnerability rating to obtain the structural vulnerability rating for wind. The wind risk index is now obtained as the hazard times the structural vulnerability rating. As shown, we have here wind risk index is hazard times structural vulnerability rating. So in this particular building, the wind risk index is about 4.19, which belongs to the category of medium risk. So using the seismic and wind risk assessment, if you have a group of buildings, you can now map the buildings, apply color codes, whether high, medium, or low risk, and you can come up with the following map. This is an example for the study conducted by the LSU and CPU. This is the map for the extreme wind risk. References for this presentation includes the PHIVOX Tools, Fault Finder, Hazard Hunter, Philippine Earthquake Model, ASEP NSCP 2015, and the research of Kirk Q in his graduate thesis. Thank you very much for your attention, and good day.